Okay, let's unpack this. Think about the last time you were, up high somewhere. Maybe you were leaning against the very edge of a high-rise balcony, looking out over the city at sunset.
Right.
Or maybe you were walking down one of those massive floating staircases in a crowded commercial atrium, or just crossing a pedestrian bridge over a busy highway with traffic rushing underneath you.
Yeah, those situations.
You probably didn't think twice about it, but in all of those moments, you were implicitly trusting your life to one specific, highly engineered piece of metal,
Yeah.
which is, the railing.
It's entirely invisible to us until the exact moment we actually need it.
Yeah.
But from an engineering and architectural standpoint, railings are actually one of the most load-critical systems in any building.
Wow, really?
Oh, absolutely. They face constant lateral human loading,
Hmm.
which basically means people leaning, pushing, tripping, and, stumbling against them.
Just constant wear and tear.
Exactly. Plus, there's the relentless environmental exposure. They are out there in the wind, the rain, the sun, all day, every day, for decades at a time.
Right. And since you sent us this guide, you specifically asked us to look into this invisible engineering holding your daily life together. So that is our mission for this deep dive.
I think it's a fascinating subject.
It really is. And the material you sent over, it's a comprehensive industry guide published by Eleanor Industries. And if we look at the guide you provided, they are a premier Indian aluminum extrusion supplier based in Gujarat.
Yes, they are.
And they lay out a blueprint for how they vet this exact manufacturing process in their own facilities. It actually gives us a great benchmark for understanding these structural shifts in global construction.
Right.
Namely, why custom aluminum railing profiles are completely taking over.
It's a massive shift.
Yeah, we are moving rapidly away from traditional materials. And to really grasp why, I think we have to start by looking at what happens on a microscopic molecular level when metal meets the elements.
Which is really the baseline for any major architectural decision. When you look at traditional materials, things like steel or timber,
Right.
you as a project manager are immediately calculating the cost of ongoing maintenance over the next 50 years.
Because it's never just a one-time cost, right?
Not at all.
Yeah.
I mean, steel is incredibly strong, yes, but even if it's galvanized or covered in a thick layer of powder-coated paint, it is fundamentally vulnerable to its environment.
Because that coating is just a shell. It's not the metal itself.
Precisely. If that protective surface coating gets scratched by a passing delivery cart,
Well,
or chipped by a heavy hailstorm, or even just degrades from UV exposure,
sure.
the raw steel underneath is suddenly exposed to the air. The rusting process begins immediately and it accelerates.
Oh, man.
Moisture gets under the edge of the coating and begins to oxidize the iron. It bubbles the paint up, flakes off, and it silently degrades the structural integrity of the entire railing system.
So you're basically locked into a never-ending cycle of sanding, repainting, treating just forever.
You are.
It becomes this massive operational expense just to keep the building safe.
Right. The material requires constant, expensive human intervention just to survive its environment. But aluminum behaves completely differently on a chemical level.
Okay, how so?
Well, when raw aluminum is exposed to oxygen, it doesn't rust and degrade like iron. Instead, it forms a microscopic, highly dense natural oxide layer right on its surface.
Oh, interesting.
And here is the incredible part. If you scratch that aluminum and break the surface, that newly exposed raw metal instantly reacts with the oxygen in the air and creates a brand new oxide layer. It regenerates.
Wait, I want to make sure I'm visualizing this correctly. Is aluminum's natural oxide layer basically like Wolverine's healing factor? Like if it gets scratched or damaged by a luggage cart, it just heals itself on the fly to stop corrosion in its tracks?
That is a highly accurate analogy, yes. It's an autonomous chemical healing factor.
Wow.
Because the barrier regenerates spontaneously the millisecond it is exposed to oxygen, the underlying metal is permanently protected without you having to lift a single finger.
That's wild.
This translates to zero ongoing maintenance costs for external applications. I mean, it truly doesn't matter if it's sitting in a highly humid tropical environment or exposed to corrosive, salty coastal air. The material fundamentally protects itself.
That alone seems like a massive win for a developer. I mean, no repainting budgets for 50 years. But I'm looking at these structural benefits, and it seems like a no-brainer until I think about the physical weight of it.
How do you mean?
Well, we all inherently think of steel as this heavy, impenetrable force, right? Aluminum feels incredibly light, like a soda can. Can a lightweight metal actually hold back a panicked crowd of people on a packed metro platform?
It's a very common misconception that sheer weight equals strength.
Okay.
What we actually care about in structural engineering is the strength-to-weight ratio.
Yeah.
A properly designed, chemically treated aluminum profile easily meets strict building codes around the world. In India, for example, the IS 875 standard governs what we call imposed loads on buildings.
Imposed loads.
Right. This standard specifically dictates the lateral force requirements for balustrades, basically testing how much horizontal pressure a railing can take before it snaps.
Got it.
Aluminum not only meets those stringent standards, it frequently exceeds them.
And the fact that it's lighter must have massive ripple effects for the actual logistics of the construction process, right?
Absolutely. Think about the real-world logistics on a job site. Let's say you're installing exterior balconies on a 40-story residential tower.
Okay.
Moving heavy, prefabricated steel components up the side of a building on a crane is dangerous. It's slow, and it requires specialized heavy machinery.
Yeah, I'd imagine.
Aluminum is significantly lighter, meaning much faster installation and vastly easier handling for the workers at height.
Which saves time and money.
Exactly. But more importantly, from an architectural perspective, it drastically reduces what we call the dead load.
Oh, I always hear that term in architecture. The dead load being the permanent stationary weight of the building itself, right? Like the floors, the walls, the roof.
Exactly. Every single kilogram of heavy steel railing you put on a balcony is a kilogram of dead load that the foundation deep in the earth and the structural columns running up the tower have to permanently support.
Oh, right.
If you can drastically reduce the weight of the thousands of linear feet of railings across a massive high-rise, by switching to aluminum, you significantly reduce the overall structural burden on the entire building.
Wow.
You could potentially use less concrete in the foundation, which saves an astronomical amount of money.
Okay, I am totally sold on the material.
Yeah.
The material itself is objectively superior for these applications. It heals like Wolverine, it's remarkably strong, it's light, and it saves serious money on the foundation footprint.
Right.
But I'm stuck on the economics of how they actually make the railings. Because if I go down to a local hardware store right now, I can buy a standard round aluminum pipe or a square tube for practically nothing. So why would a massive developer go to a specialized company like Eleanor Industries in Gujarat to have them custom forge entirely new shapes?
Right.
Isn't that just throwing money at aesthetics?
It seems like it would be, but it's actually about structural integrity and long-term costs.
Okay, explain that.
Standard sections, those off-the-shelf round tubes or flat bars, they have severe engineering limitations. A standard tube is fine if your budget is incredibly tight and your aesthetic requirements are basic, but think about how a railing actually works.
Right.
It's almost never just a single pull. If you want to attach a heavy glass panel to that standard pipe or run tension cables through it for a modern look, how do you do it?
I guess you'd have to, drill holes in the tube, weld on a bunch of mounting brackets, and bolt heavy metal clips to hold the glass.
Precisely. It becomes a messy, complex assembly of third-party hardware. And every single time you drill a hole into a standard pipe, you create what engineers call a stress concentration.
Stress concentration.
Right. You are artificially weakening the metal exactly where it needs to bear load. Plus, you are creating tiny gaps where water can pool, freeze, and expand.
Oh, wow. Wait, so the engineering isn't in the screws or the bolts holding the railing together? The engineering is baked into the actual physical cross-section of the metal before it even arrives at the site?
Yes. What's fascinating here is the sheer capability of the aluminum extrusion process to eliminate all of those drilled holes and weak points.
How does that process work exactly?
Well, extrusion is essentially taking a massive, solid billet of raw aluminum and heating it until it's pliable. Not melted into a liquid, but soft, like heavy clay.
Okay.
Then they use a massive hydraulic press to force it through a custom-cut steel die. Imagine pushing dough through a star-shaped nozzle to make churros, but with thousands of tons of hydraulic force and solid metal.
That is a great image. So instead of drilling holes and bolting ugly brackets onto a standard round pole, a custom extrusion is basically born like a 3D puzzle piece.
Yes.
It's already perfectly shaped to hold glass or route cables without any extra hardware.
Precisely. An architect can design a single cross-section of metal that features multi-void internal chambers for immense structural rigidity. And it can have integrated clip channels on the sides to hold thick glass perfectly in place.
Wow.
And internal grooves at the bottom for routing LED lighting wires seamlessly. It's all one continuous, flawless piece of metal straight out of the press.
That is brilliant.
There are no bolts to rust, no brackets to fail, no drilled holes to weaken the structure.
Amazing.
And beyond the structural benefits, custom extrusion guarantees what we call architectural finish consistency.
Okay.
If you are building a premium residential tower, you want the railing profile to perfectly match the aluminum window frames and the facade panels. If you custom extrude the railing from the same supplier, using the exact same alloy batches and the same surface treatments, they match flawlessly.
That makes total sense.
Plus, if you're building a high-volume residential program, say 1,000 identical apartments,
Right.
the upfront cost of cutting that custom steel die is amortized so quickly over the sheer volume of metal that it actually becomes incredibly cost-effective. You save thousands of labor hours on installation because everything just snaps together like Lego.
Okay, so we have the perfect 3D puzzle shape, and we've eliminated the weak points. But having the right shape doesn't automatically mean the railing won't bend when a panicked crowd leans against it.
No, it doesn't.
That comes down to the invisible chemistry of the metal itself, right?
The source material dives really deep into the specific alloy and temper grades used in this industry, and it seems like a delicate balancing act.
It is entirely about chemistry, and it's very precise science.
Yeah.
Commercial aluminum isn't just pure aluminum. It is always alloyed with elements like magnesium and silicon to drastically change its physical properties.
Oh, I see.
In the architectural railing world, there are a few primary players. The most common one you will see is the 6063 T5 alloy.
6063 T5. Okay. This is considered the architectural standard. The guide notes it has a tensile strength of about 185 megapascals.
Which, for those of us who don't speak material science, what does that actually mean?
Fair point. Let's translate that into human terms.
Please.
Megapascals measure how much pulling force a material can take before it physically breaks. To visualize 185 megapascals, imagine a single square inch of this aluminum, just a tiny cube.
Okay, I'm picturing it.
You could hang a weight of about 26,000 pounds from that single 1-inch cube before it would snap.
That is massive. I mean, that's plenty strong for your typical residential balcony or an interior atrium staircase.
Correct. But its real superpower isn't just strength, it's extrudability. Because of its specific chemical makeup, you can easily push 6063 T5 through a complex die to create those incredibly intricate multi-void 3D puzzle shapes we talked about.
Oh, right.
Complete with perfectly sharp, crisp corner radii. But if you need more strength, you step up the chemistry to 6061 T6.
The heavy-duty option.
Exactly. 6061 T6 bumps the tensile strength up to a roughly 310 megapascals.
Okay, let's use our cube analogy again.
Yeah.
If 185 megapascals is 26,000 pounds, 310 megapascals means that same tiny 1-inch cube can now hold nearly 45,000 pounds.
Exactly right.
That's like hanging 2 full-size, loaded school buses from a piece of metal the size of a postage stamp.
It's an incredible amount of strength. You use this heavier-duty alloy for high-rise external balustrades facing extreme hurricane wind loads, heavy crowd control barriers in public stadiums, marine environments,
Right.
and critically, in seismic zones where the metal needs to exhibit specific ductility, meaning it can bend slightly without snapping under extreme sudden stress like an earthquake.
Wow.
And then there is 6082 T6, which is a premium structural option. It has excellent weldability and even higher strength, very common in European markets and available on order from top-tier global suppliers.
Okay, here's where it gets really interesting to me. Looking at these numbers, if 6061 T6 is almost twice as strong as the 6063 alloy,
Yeah.
why wouldn't a developer just use 60 or 61 for absolutely everything? I mean, why would you ever sacrifice strength when you're dealing with a literal life or death safety feature like a high-rise balcony railing?
It is a brilliant question, and it comes down to the fundamental trade-offs in metallurgy.
Okay.
When you increase the strength of the alloy by changing the chemistry, like adding more magnesium and silicon,
Yeah.
you decrease its extrudability.
Ah. The metal is physically harder, so it gets harder to push it through that star-shaped dough nozzle.
Exactly. 6061 T6 is a much tougher, stiffer metal, even when heated. If you try to force it through a die that has very intricate, delicate internal channels or razor-sharp architectural corners, the heavy metal resists.
Makes sense.
The delicate parts of the steel die wear out significantly faster, and the aluminum profile itself might warp and fail to hold those tight dimensional tolerances we need for snapping the glass in.
Oh, that would be a disaster.
Furthermore, the molecular grain structure of the 6061 alloy doesn't take surface finishes nearly as cleanly as 6063. 6063 gives you that flawless, mirror-smooth base, that architects absolutely crave for premium visual applications.
I see.
So the rule of thumb is you don't over-engineer the chemistry if you don't need to. You perfectly match the alloy to the specific mechanical and aesthetic demands of the environment.
So 6063 gives us this incredible complex shape and a smooth finish. But raw aluminum, even with its Wolverine healing factor, is going to look like a dull industrial gray after a few weeks of weather exposure, right?
Yeah, definitely.
If an architect is designing a billion-dollar luxury hotel, they need that metal to look like brushed bronze or champagne or matte black.
Right.
How do you change the color of the metal without ruining that regenerative oxide layer we just talked about?
It's a great point.
The Eleanor guide outlines 3 main finishes: mill, powder coating, and anodizing. Mill is just the raw, unfinished extrusion, which makes sense. I mean, you'd rarely use it unless it's a hidden industrial part inside a wall. But powder coating and anodizing seem to be where the magic happens.
Yes, and they function in completely different ways mechanically. Powder coating is a fascinating process. It involves applying a dry paint powder to the metal and then baking it in an oven at high heat to cure it into a hard skin.
But how does it stick to the metal smoothly before it bakes? If it's just dry dust, wouldn't it just fall off?
It uses electrostatics. In the factory, they give the raw aluminum profile a strong negative electrical charge. Meanwhile, the dry paint powder gets a positive electrical charge as it is sprayed out of the gun.
Oh, wow.
Because opposites attract, the metal literally acts like a massive magnet.
Huh.
It actively pulls the paint powder into every single microscopic corner and crevice. It even wraps around and coats the back of the metal without the sprayer having to aim there.
That's so clever.
It ensures a perfectly even coat before it goes into the curing oven. When applied properly over a chromate or anodized pretreatment, powder coating offers immense UV stability and can be formulated in literally any color in the RAL or NCS global color matching systems.
That makes perfect sense. It's essentially an incredibly tough, durable layer of plasticized paint that sits on top of the metal.
Right.
But then there's anodizing, which honestly sounds like science fiction to me.
It kind of is.
The guide notes standard anodizing is 15 to 25 microns deep, but for harsh marine environments, they do a hard anodizing at 25 to 50 microns.
Yes.
To put this in perspective, is powder coating like putting a really tough, colorful phone case on your metal, whereas anodizing is like actually altering the molecular structure of the phone itself so the metal becomes the armor?
That is exactly the distinction. Anodizing isn't paint at all. It is a highly controlled electrochemical process.
Okay, how does that work?
In the factory, you submerge the raw aluminum in a massive tank filled with an acid electrolyte bath, and you pass a powerful direct electrical current through it.
It's like a battery?
This current literally rips oxygen ions out of the water and forces them to combine with the aluminum on the surface of the metal. You are artificially, drastically thickening that natural Wolverine healing layer we talked about earlier. You are growing an armor layer out of the base metal itself.
So it's not a coating sitting on top, it is the metal itself transformed.
Right. And because of that integrated grown nature, anodizing physically cannot peel, chip, or delaminate the way a painted coating can if it's struck hard enough.
Wow.
Plus, during this acid bath process, the structure of that newly grown oxide layer is highly porous on a microscopic level. It looks like a honeycomb.
Okay.
Before they seal the metal, manufacturers can introduce specialized metallic dyes deep into those microscopic honeycomb pores, resulting in stunning colors like silver, champagne, bronze, graphite, or pure black.
Oh, that's how they color it.
Exactly. They then boil the metal in water to permanently seal the pores shut.
That is incredible. The color is literally locked safely inside the molecular structure of the armor itself.
Precisely. It's incredibly resilient against fading from UV rays, it withstands acidic cleaning products, and it handles heavy physical wear.
That totally explains why the railings in a premium commercial interior or an airport or a high-end mall look so flawless even after thousands of people drag their hands across them, complete with rings and watches every single day.
Exactly.
So now we know the exact structural, chemical, and aesthetic profile of a perfect railing system. But how does a project manager actually ensure they are buying from a manufacturer who can pull this off? Because making a flawless 3D puzzle piece with molecular armor seems like a very tall order for an average factory.
If we connect this to the bigger picture, the harsh reality of global construction is that perfect specifications on a piece of paper mean absolutely nothing without the physical manufacturing capability to actually execute them.
Right, of course.
When we look at the Eleanor Industries guide, it serves as a very practical real-world benchmark for vetting a supplier's true capabilities.
Because not all extrusion plants are created equal. Just because they have a hydraulic press doesn't mean they can make a skyscraper railing.
Far from it. First, you have to evaluate their press capacity. In the industry, this is measured by the profile's circumscribed circle diameter.
Circumscribed circle diameter.
Right. In simple terms, if you draw a circle around the absolute widest points of your custom railing cross-section design, the manufacturer's hydraulic press must be physically massive enough and have enough tonnage to push that much metal through the die uniformly.
Ah, I see.
Many smaller suppliers simply lack the heavy-duty presses required for thick, complex architectural profiles.
The guide also hammers really hard on the concept of alloy traceability.
Which is completely non-negotiable for securing building permits and engineering sign-offs.
Really?
Oh yeah. If a supplier says they use the heavy-duty 6061 T6 alloy, they must provide certified, third-party material test reports proving the exact chemical composition and mechanical yield strength of that specific batch of metal.
It's a huge liability issue.
Exactly. If a balustrade fails and someone falls because the alloy was secretly diluted with cheap scrap metal, the liability is catastrophic.
Wow. There is one point in the supplier vetting section I really want to ask about. The source heavily emphasizes the importance of in-house die design.
Yes.
Why does that matter so much? Couldn't a supplier just cheaply outsource the manufacturing of the metal mold to a third-party toolmaker to save money?
They certainly could, and a lot of cheaper suppliers do, but outsourcing introduces a massive quality variable.
How so?
Think back to those hardware-free connections we discussed earlier, the intricate slots and internal grooves where the heavy glass panels slide in perfectly without needing bolts.
Yeah, the 3D puzzle pieces.
Exactly. Those require incredibly tight dimensional tolerances. We are talking about precision down to fractions of a millimeter. If the die design is outsourced, and the toolmaker ships it back and it's slightly off by half a millimeter, the supplier might try to push the metal anyway just to meet a deadline.
Oh, yikes.
But if the die design and manufacturing are entirely in-house, the actual engineers who design the profile are the ones cutting the die and testing the first extrusion on the factory floor.
So they can catch the mistake immediately.
Exactly. They can adjust and refine the die right then and there to guarantee those microscopic tolerances. It is truly the only way to ensure the final product actually snaps together on the job site exactly the way the architect imagined it.
That makes a lot of sense.
A vertically integrated supplier controls the metallurgy, the complex geometry, and the finish all under one roof. That is exactly what project managers look for when vetting a partner for major infrastructure projects like metro stations or massive residential high-rises.
So, what does this all mean? We started by talking about leaning against a balcony, trusting a piece of metal.
Yeah.
I think the core takeaway here is that the railing holding you up isn't just some raw, dumb bar of steel chopped to length.
Definitely not.
It is a highly specific, chemically tuned, custom extruded piece of safety engineering. It has an autonomous Wolverine healing factor. It's designed on a molecular level to hold incredibly complex geometries without weakening, and its very surface is grown into a colored structural armor.
It really is a marvel.
A genuine marvel of invisible engineering.
It truly is. And understanding the extrusion process, this incredible ability to perfectly tailor a single structural element to do 5 different jobs at once, eliminating hardware and weak points.
Yeah.
This raises a really important question for the entire future of architecture.
Wait, I think I see where you're going with this. If we can extrude a railing that perfectly holds glass and wires without a single screw?
Exactly. Right now, custom aluminum extrusion replaces traditional multi-part railing assemblies. But as the hydraulic presses get vastly larger in the coming decades, and as we develop even stronger aerospace-grade alloys, how long until we move beyond just railings?
Oh my gosh, we could extrude entire building facades or even modular structural rooms. You could just extrude a single smart multifunctional room component with all the wiring channels and window frames already baked into the metal shape.
Precisely. We could potentially completely eliminate the need to construct buildings piece by piece, bolt by bolt, and instead just snap vast, perfectly extruded architectural geometries together seamlessly on site.
That is a staggering thought. Building a skyscraper by snapping it together like a massive high-strength puzzle.
It's the future.
Next time you find yourself high up, leaning against that cool, perfectly smooth metal railing on a balcony, just think about the sheer amount of molecular engineering keeping you safe and wonder what else they might be extruding next. Thank you for joining us on this deep dive into the hidden systems around us. Keep questioning the world you walk through. and stay curious.